Hello, and welcome to this talk on Presto at Facebook. We will talk a little bit about the problems we are facing at Facebook with respect to the data explosion. How are we evolving Presto to solve some of these problems, and a few updates on specific projects. So let's start with the basic problem statement. Data is exploding at Facebook and everywhere else. So here are some rough numbers on where we are at Facebook. We are getting triple-digit petabytes of data replicated daily. Our warehouse is crossing multiple exabytes. We have millions of cores providing compute on this data, tens to hundreds of thousands of pipelines, thousands of people writing these pipelines and writing dashboards and other artifacts on top of this data. Our pure shuffle volume is into triple-digit petabytes per day. And of course, our stream processing is rapidly becoming more and more popular. We're already processing multiple terabytes per second of streaming data. So that is one of the big problems. But along with that, we have a host of other challenges that we have today. As data is becoming more and more important, freshness of the data, how quickly can we create actionable insights, which also means both data needs to be fresh and queries on the data needs to be fast. How are we standardizing and converging our data stack so that our users can be highly productive and don't have to have a steep learning curve every time they want to move from batch to streaming, from interactive to batch, to do graph processing and all that stuff. Exporting analytics is a new and upcoming trend where we want to make analytics available directly to the end users and our customers, external customers like our advertisers, page owners, and even our end users want to know how their ads are doing, how their pages are doing, and so on. Next is privacy and security. As everyone is well aware, this is becoming a huge motivator for data. We want the data processing and the flows to be completely privacy safe and secure so that we can protect our customers and our users' information and do not use them for means that they were not supposed to be used. Auto-awesomization. This is, I guess, a somewhat cheeky term that we have been using. We have heard this being used in different aspects, like autonomous warehouse, self-tuning databases, and so on and so forth. But the basic concept is simple. The database, or the warehouse in this case, or the data stack, needs to become smarter and more self-aware so that our users can simply talk about what they want to do and not how they want to do it. So in other words, we want to abstract away a lot of the common concepts around partitioning, around query optimization, about data placement, and so on and so forth. Next is complex data models. Increasingly, our data can no longer be represented in simple normalized 3NF or BCNF or Kimball or Inmon style data models. There is a lot of complexity in the data. We're talking about semi-structured, time series, geospatial, complicated nested relational data structure that indicate relationships, graph models, and so on and so forth. And with these models comes the requirement to create richer and richer methods to query this data. So the old SQL of simple join and scalar columns and aggregations and window functions is no longer enough. We need to increasingly provide richer and more complex methods in the hands of our users. Let's also take a minute to talk about the environmental trends. So one big one is disaggregation, which means that our storage and the compute need to be disaggregated. This was pioneered by Dremel and BigQuery, and then by Snowflake, and increasingly all the big data stack in moving in this direction. Co-locating compute and storage at this point is widely regarded as a bad idea, and for good reasons. So we need to take care of that. The important thing is that in the process, we must not sacrifice flexibility and feature sets and performance and so on. Horizontal scaling. Moore's law is dead, or so everybody says, which means that we need to be able to scale with the data by adding machines horizontally and not just by vertically scaling. We can no longer go from 256 GB to 1 terabyte to 4 terabyte machines. We have to add more machines. These machines will be elastic in nature. In other words, they might come and go. We might get heterogeneous machines and so on and so forth. Power. Power is a very critical resource these days, not only because of the green world, but simply because power is unavailable at the scale that we are talking about. And we need to make sure that our compute is increasingly optimizing not just for CapEx, in other words, how much money we spend to buy the machines, but also in terms of power. Like, what can we get out of every wattage of power that we consume? Global optimizations. As our warehouses are becoming bigger and bigger, local optimas no longer hold. We need to make sure that the entire warehouse, which is this multiple exabytes of data spread over many, many regions, is constantly being globally optimized and not only optimized in terms of how much energy can I, or how much compute can I get out of the single machine. And finally, this is super important, engineering efficiencies. We cannot really scale the engineering team proportional to the amount of data and the complexity. As the data grows by 10x, it is not really feasible for us to hire 10x the number of engineers or 10x the number of SREs or production engineers to continue to take care of our clusters. We must automate more and more. We must make things simpler and more efficient to increase our velocity and do more with less people. So in other words, I was reminded of this album, which was one of my favorite albums. We need to get bigger, better, faster, and more. So let's talk about how we are doing that with Presto. And I will use Presto as an example because Presto is one of the most popular query engines at Facebook and elsewhere. But this applies, most of these principles apply to the overall data stack at Facebook and probably in many other similarly sized companies. So on the left-hand side, I think are the 4 themes we talked about: bigger, better, faster, and more. And on the right-hand side, there are a few specific projects that we're doing to make Presto better along these 4 axes. So let's start by discussing these projects and how they make Presto bigger, better, faster, and more. So first, we'll talk about Presto on Spark. This is a very interesting project that we are doing, which is right now, productionization is in progress for this project. The important thing about this project is that we realized that we are trying to solve a problem that is already solved. In other words, we needed to make Presto, which has a query dialect that most of our users prefer, to run in Spark mode. And the reason we want to do that is scale. We know that Spark has been optimized for operating at a really, really large scale. For example, it has fine-grained checkpointing at the individual split or worker level. It can do really, really large shuffles. It can handle job with millions of splits and so on and so forth. It has a nice query isolation model. So we can run a separate Spark job for every query so that if a query fails or crashes, it doesn't impact the rest of the clusters. Now, these were some of the problems that we were trying to solve with Presto, whereas we also have a fairly large Spark team in-house. And our thought was, hey, let's see what we can do together. So it turns out that what we can do together is something really exciting, which means that we can provide 100% Presto compatible SQL dialect, which enables the user to seamlessly go from interactive to match queries, but give them 10x the scale, give them all the features of Spark that they know and love. In other words, we can do split level checkpointing and retry. We can do job level isolation. We can reliably run jobs that run for many, many hours or even days. We can share the batch cluster resources between Presto users and Spark users. This is a really big deal. It enables us also to run on our elastic compute that we have talked about elsewhere. In other words, Facebook, for example, has the equivalent of Amazon Spot instances where the machines can come and go at any time. And as you know, Presto today cannot easily recover from individual machine failures, which makes these machines really hard to use in the Presto context. But with Presto on Spark, we can really easily use these machines and get massively scalable performance while retaining all the language features of Presto and full compatibility with Presto. Disaggregated coordinators. So today, Presto has a single coordinator as a bottleneck. This has numerous problems. If the coordinator freezes, the entire cluster freezes. We cannot handle too many queries at once because the queries are bottlenecked by the resources available in a single coordinator, and so on and so forth. With the disaggregated coordinator project, internally we call it Fireball, we are able to scale Presto to much, much larger clusters. The way it is designed is that we allow the query coordinators to scale horizontally while still having a centralized resource management. The resource manager is still kind of replicated, so we have no longer a single point of failure. The entire cluster is highly available. It completely eliminates coordinator scalability limits. So we can now run clusters with thousands of machines and hundreds of query coordinators and scale to thousands of queries per second. It cleanly segregates the resource management and query coordination functions. It reduces resource fragmentation, and it isn't currently feature complete. And we are shadow testing this with a hope to launch early in the next quarter. PAC, the intelligent workload placement. One very common problem that we have been seeing in Presto is that the current place-fail logic is not very smart. In other words, when a query comes in, the individual splits of the queries are more or less randomly distributed across the workers. This has a lot of issues. It does not allow the worker or the cluster as a whole to be fully utilized because some clusters might be memory heavy, some workers might be memory constrained, some workers might be CPU constrained, some workers might be network constrained, and so on and so forth. In certain cases, we also need affinity so that a given task for a given file always goes to the same worker as the primary or the secondary. So the core idea behind PAC is to make sure that the cluster is self-aware. In other words, the resource manager knows which workers are in which state. With this change, we are able to see more than 20% improvement in the throughput of large-scale clusters during testing. And it is also resulting in significantly better reliability and stability of the clusters. There are fewer workers which are going out of memory. We are seeing fewer query failures. We are seeing overall much better utilization and smooth utilization of cluster CPU and memory. Again, this is mostly feature complete. We are shadow testing this, and we intend to launch this in Q3. We talked about auto optimization. Now, there are a number of things we are doing here, starting from speculative execution, which is particularly interesting. So today, one of the common things that happen is that a Presto query gets stuck because it is waiting for that one last worker to finish its task. With speculative execution, we can actually redo the split level retry at the leaf level for certain workers, which means that if one worker is stuck and 99.9% of the workers have finished, we can send that split again to a different worker and take whichever comes first. This is an early prototype, but the results are pretty promising. We are, of course, continuing to improve our statistics gathering with the cost-based optimizer to make the optimizer smarter. But more importantly, we are working on history-based optimizations, which are really exciting because it allows the query engine to continuously become smarter as more queries get executed on it. The core idea is that as queries get executed, we collect statistics about the operators to know, hey, which part of the query, for example, had how much cardinality. And we use that. So when we see the query again, or we see a very similar looking query, we're able to use that to make smarter decisions around join types, join order, join parallelism, aggregate parallelism, and so on and so forth. The last one is around adaptive execution. This is a very early stage idea that we are working with. But again, the core idea is that today's Presto execution graph is kind of fixed. So once the query starts executing, you cannot change it. Adaptive execution is going to introduce interesting concepts in the execution tree so that the query can use the statistics gathered during the initial parts of the execution to dynamically change the ordering type or parallelism of subsequent operators so that the overall query optimizes itself continuously as it runs. So one of the important things that we have been finding is that the query engine itself is not really enough in terms of going to the maximum optimization. We actually need to optimize the system as a whole, which means that the data, the metadata, and the query engine needs they all need to work in tandem to provide the best possible performance and efficiency. So to this end, we are doing a number of improvements. We are experimenting a lot with file formats. For example, we have a new prototype file format that is showing significantly better performance for ML workloads. We intend to use that for analytics as well. We are adding a lot of rich metadata to our metadata server. We are enhancing Hive metadata store significantly so that we can use this rich metadata for better query processing. Smarter readers and writers. One good example of this is the ARIA project, where we significantly changed the readers to push down filters and projections way down into the reader stack. And that had significant improvements in terms of latency and efficiency. Similarly, during writing, we can decide in what order to write the columns and the rows to get maximum bandwidth out of the IO that we have. And that also enables much better caching, for example. Materialized views and Z-order partitioning are two other data optimizations that we're introducing to reduce the amount of data we need to read to answer a query. These are fairly well-known techniques in the industry. We haven't had them so far, and we are implementing them. Usage-based layout decision essentially is a concept by which we continuously monitor what the data is being used in what form. In other words, which are the most frequently used columns, what are the most frequently used filters, what are the most frequently used columns you're grouping on or joining on, and things like that, and use that to first manually suggest to users how to lay out their table, and then subsequently to automatically relay out the table based on these decisions. So Raptor, let's talk a little bit about the RaptorX project, which has introduced significant performance improvements to Presto. And the basic idea is around caching and affinity. So as we said earlier, one of the important trends that we have is disaggregation, which means that the storage is separated from the compute. Now, this introduces a challenge where how do we get the same performance that we were getting out of local SSD or in-memory, for example, databases, while your storage is actually on a remote HDFS or S3 cluster. And the basic idea behind this is essentially tiered caching. So starting from the coordinator, where we have introduced caching for metadata, stats, ACLs, and various other things, to the worker, where we have introduced caching for data footers and the actual columnar data, and even partial results, we are increasingly moving towards a world where even with disaggregated storage, we can actually get equal or even better performance than we can get with a storage that is combined with the compute. And this is mainly because of this fairly standard insight is that the hot data tends to be much smaller than the whole data set. In other words, in real life, what we have seen is that with less than 10% of the cache size of the actual data, we are able to keep 90 to 99% of the queries not going to remote storage. There is another big advantage of this. Because the storage is disaggregated from compute, should one of the workers get stuck, you can do speculative execution in a secondary worker and still get really good query performance, especially at the tail. Based on the initial numbers, we are seeing up to 10x better performance than the disaggregated Presto model, and it is as good or better than the old co-located storage and performance engine that we had with Raptor. Let's talk a little bit about Velox. Now, one of the fundamental things that we realized early on while looking at what can we do with the next generation of Presto is that our worker core library that does the evaluation, in other words, that does the actual reading, filtering, joins, aggregations, and all these core operations, is kind of reaching its limits in terms of what we can do with it. So it's written in Java. There are a lot of memory issues with Java. We are not able to fully utilize SIMD and kind of cache hits and other optimizations. So what can we do there? And we took a really bold decision. We said that, you know what, we are going to rewrite this from scratch in C++. And this is not a very unique decision. Many other teams have come to the similar conclusion. For example, Databricks is doing the same thing with Photon. So we said we are going to rewrite this thing in C++, and we are going to write it in a way so that it can be reused by many different agents. So we are developing Velox, and Velox is this core component, is a C++ library that can be embedded in Presto or Spark or Flink or any kind of engine to essentially accelerate these core operators. So it's written from scratch in C++. It uses the state-of-the-art vectorized and code gen techniques. So this is a hybrid engine, which is predominantly vectorized, but we also have hooks where, for example, complex expressions can be code gen and hooked into this library. Based on the early results, we are seeing some really, really promising gains, anywhere between 2 to 10x speedups on the patterns that we support so far, and we are adding more and more operators. So hopefully this trend will hold. We expect to publish this to open source fairly soon. Right now, it is running end-to-end on Presto, Spark, and our internal streaming engine in Facebook. And this is expected to hit production early next half. So let's talk about SQL portability and power. One common complaints that we have often heard from our users is that we have too many dialects of SQL at Facebook. And this is probably true of other companies as well. The Spark, Presto, Flink, internally we have Kubrick, Raptor, Scuba, Presto, of course, Spark, Puma, and so on and so forth. And all of these, in theory, suggest that they should be portable because they all support SQL. But as we all know, SQL is a very loose and open standard. And it turns out that it is really hard to port queries from one to the other. And this was a huge productivity killer for our users. So we have started this other fairly bold project, which is called CoreSQL. And the core idea behind this project is portability, which is to say that if you know CoreSQL, you should be able to write your query once and run it unchanged everywhere, whether you're doing it for interactive queries on Presto or batch queries on Spark or streaming queries on Xstream, or in fact, even OLTP queries or machine learning queries through in other parts of Facebook. The second important goal of this project is to make SQL richer, as we have talked about before. SQL and its kind of current or legacy form, it's hitting its limits. And we want to really have a much, much richer SQL, which has portable UDFs, which we'll talk about next, much richer type system. It allows graph queries, streaming queries, and so on and so forth. SQL functions, for example. So what we have decided is that we are going to standardize on Presto SQL as the basis of CoreSQL and evolve it by adding extensions for all of these things. And as of now, today, we have, as part of Presto and Spark, CoreSQL running on Spark and in production on a small number of pipelines. In other words, you can write the same query and run it interactive in Presto or in batch mode through Spark, and it will produce identical results. We are in closed beta for streaming, and we are fairly close to production in terms of graph. This is called Graph SQL. And finally, one big part of CoreSQL is also how do we go beyond SQL and incorporate functionality that must be expressed in procedural languages. We have a lot of functions written in C++, Java, Python, Hack, and we want to make sure that any functionality that is there, we should be able to wrap it once and run it in any mode, whether it is Presto, Spark, streaming, and so on and so forth. So we have created this framework called Portable UDFs. And what this allows you to do is to run this code unchanged as an out-of-process server. We have introduced an efficient transport protocol using the Presto page, which is similar to Arrow. We can also potentially inline this. So if your host, for example, your Java execution engine and your target is also Java, then you can actually inline that and run it in process. So right now it is running in Presto and Spark. We plan to make this available in streaming and other places as well. And we are continuing to improve its performance, adding support for more languages, and so on. So finally, I wanted to leave a few thoughts. Whether it is in OSS or in Facebook, one of the feelings that we continue to have is that sometimes we have too many options. So if we look at SQL engines, we have Presto, Spark, internally we have Kubrick, Scuba, and so on and so forth. SQL dialects, again, we have Presto SQL, HQL, PQL, and so on and so forth. Different modes, streaming, batch, interactive, graph, many meta stores. Like inside Facebook, we have Hive meta store, which we have significantly enhanced. We also have outside Facebook, Iceberg, Delta, Hoodie, and so on. Similarly, with formats, internally we have ORC in our internal extensions to ORC, which we call Dwarf. Externally, we also have Parquet. New formats are coming in all the time. So can we accelerate through consolidation? In other words, when we have too many of these things, it becomes really hard to innovate because now we have to add support for all of these things, and the user has to learn how to work with all of these things. So sometimes less is more. And one of the things that we are working on at Facebook is figuring out how to consolidate to have fewer options, which makes our users' life simpler, but also our life simpler because we don't have to add support for so many different aspects of so many different things. So with the Facebook mission for Presto, this is my final slide. We want to create the fastest and most dependable industry standard data analytics engine, fully open source. We want to provide our users with an incredible, awesome experience. And we want to have an open and growing community. If you're excited about this, come join us. We are at fb.com/carriers. And we also have a carrier booth at Sigmod, which you can go directly from here. Thank you and have a great day.